Yeah, good morning. Before I start with a new topic, namely computation tree logic, there is one question which popped up in the lecture last week that I would like to address because I think it's important for your understanding. And I thank the students for posing this question because I think it was a very relevant question. So let's go back to what we were proving in the last lecture. We were proving that actually LTL model checking is p-space complete. Yeah, and this proof consists of two parts. So actually what we did is, because p-space is the same as its complement, we were not looking at the LTL model checking problem. It's an LTL model checking problem. But we were looking at the complement. So this holds if and only if the complement, which is the existential LTL model checking problem, is p-space complete. Why did we prove this? This is because we know that p-space is the same as co-p-space. So this was the problem we were considering. And in order to prove this, we did actually two things. So we have to prove that this problem, so the existential LTL model checking problem, is in p-space. And secondly, we have to prove that this problem is p-space hard. Good. How did we do this? I showed you this in quite detail by means of this acceptance problem for deterministic Turing machines. And that was a detailed construction that we showed last time. And I also showed you the first thing, and actually what we proved is not exactly what is written down here, but we used the fact, and that is because p-space is the same as np-space. Np-space stands for, it suffices to have a non-deterministic computation, which you can do in polynomial space. So actually what we showed is that the existential LTL model checking problem belongs to NP space. Okay, so that's the issue. So that was also on the slide. So that's where this comes from. The question, is there a path such that pi satisfies phi, is the same as the existential LTL model checking problem for the negation of a formula if you interpret this as something which is a negated formula. So the way I explained to you this is that you can solve this by this non-deterministic polynomial space-bound algorithm. And the idea is that you guess non-deterministically some kind of computation or part of the product of the transition system and the Büchi automaton. Now, what's now the issue? This Büchi automaton is, as we have seen in the construction, exponential in the size of the formula. Yeah, so it's not immediately clear why this can be done in polynomial space, and that's what I'm going to address in a minute. So what was the idea? We're going to guess a part in this product such that you start in some initial state. At some point you reach a cycle, and this cycle is an accepting cycle in the product. And then we have to check whether this part that we guessed is an accepting part of the Büchi automaton. And how do we do this? So we guess two numbers. So after having guessed a part, we guess two numbers, where these numbers are linear in the size of the transition system, but exponential in the size of the formula. Yeah. And this is necessary because this has to do with the number of acceptance conditions that we need to check. And remember from the construction that for every sub-until formula you have an acceptance condition. So how many acceptance conditions do you have in the worst case? Linearly many in this size of the formula. Good, and then what we do is we guess this part in a transition system. We guess a couple of elementary sets. Yeah, so those B's are all elementary sets. Yeah. So it's important I don't construct the Büchi automaton, right? I'm just guessing a sequence of states in my transition system. I'm guessing a sequence, maybe exponentially many, but I'm going to guess such a sequence of elementary sets. Actually, I'm checking sets of the closure. I need to check whether they are elementary. And then I check the following conditions. I need to check whether I close somewhere this state and that state is the same as those two. And I have actually an initial run. I need to check that this is an initial run for the trace in my G, B, and A. And I need to check whether I fit all the acceptance conditions. Good. If this is the case, then we return yes, otherwise we return no. Yeah? So what do we all need to check? So the point I want to make is the following. All these checks can be done in polynomial time. Or polynomial space. Sorry. Yeah, that's the important point. Yeah? So although the intuition of this construction is indeed driven by this Büchi automaton, which is exponentially the size of the formula, you can do the checks in polynomial space. For instance, what do we need to check? We need to check that, for instance, in order to check whether we have a finite path, we need to check that Si is a successor of Si minus 1 in the transition system. Then we need to check things like the B's that I select are elementary. So I indeed take a set of subformulas from the closure, but they also need to be elementary. Yeah, because otherwise it's not an initial run of my Büchi automaton. No? Then third, what I need to check is that there is a transition, so I need to check that Bi intersected with AP is actually the labeling of Si. And I need to check that Bi is a successor of the previous one, that means Bi minus 1 together with the labeling of Si for I at least 1. And what else do I need to check? I need, in addition, to check the acceptance condition. So this is this last bullet. So how can I check this? Well, you just keep track. So basically what we have to check is this last condition. I just write it down. Psi2 such that psi1 until psi2 belongs to one of the Bi's between n and n plus m. Yeah, so one of the Bi's on the cycle. This is a subset of all the Bi's. Yeah. N plus m. Good. So how are we going to do this? We're going to remember the subformulas that occur at those elementary sets, so that are contained in these sets Bn up to Bn plus m, I think minus 1, plus 1. And we're going to do the same for all the psi2s plus all, so we remember all the psi1 until psi2, and you remember all psi2s occurring in these sets. So what do we need to check? You only need to keep track of something which is a successor or predecessor. You need to check this, you need to check this condition, you need to check this condition, which is again all relevant between a predecessor and a successor. but you never store the whole path. Yeah, that's the crucial thing. In particular, you don't store the whole cycle. Yeah, notice this cycle is of exponential length, because m is at most k, and k is exponential, but you don't need to store the whole cycle, because the only thing that you need to do is you have to check condition 5, and you can imagine that I just have a sliding window over the cycle. Every time I take a new state, I just increase the set of these until subformulas, and I increase those size. And this can all be done in polynomial space. Yeah? Good. I think the point is that this slide is a bit misleading in the sense that it suggests that you first generate the whole Büchi automaton and then do the whole checks there, and that's not the case. Good. I hope I have clarified this, and thanks for the question. Good point. Okay. Good. Then I would like to start today with a new topic, and that is computation tree logic. So what we have seen so far were linear time properties. In the beginning we said there were sets of traces, and then we said, well, this is maybe a bit awkward, why don't we introduce a logic? So we have LTL. And now I'm going to introduce you yet another logic. So the first question you should pose is why? Yeah, why yet another logic? Is one logic not enough? Yeah, and the answer is no. So what we're going to see is that this logic CTL has an incomparable expressive power with LTL. So I write this down as a Venn diagram. Suppose these are all the properties that you can express in LTL. Okay, so this is an LT property. This is an LT property, and so forth. Huh? So this circle is the whole set of properties that you can express in LTL. Now I'm going to introduce the logic computation tree logic. Computation tree logic is due to Alan Emerson and Edmund Clark, both Turing Award winners in 2007. Emerson at that time was a PhD student of Clark, and they introduced a logic that's called CTL, and this logic, in this Venn diagram looks like this. What does this mean? It means we are going to see certain properties. They will not be LT properties anymore, but they will be properties about trees. This is linear time, right? These are sequences. Remember, we had infinite sequences of set of atomic propositions. We're going to make a paradigm shift. Rather than having a linear time perspective, we're going to take what they call a branching time perspective, which means that the basic notion will be a tree. An infinite tree. Yeah? And that was the notion of CTL. So actually these are infinite trees in some sense. Yeah? And we're going to see that there is a common subset. So there are properties that you can express in LTL that you can also express in CTL, but the two logics are incomparable. So there are certain properties like this one here that can be expressed in LTL but not in CTL, and vice versa. Yeah? Good. So that's one good thing to know. Then what we're also going to see that there are certain problems here that you maybe can express in both logics, but in one logic you can express a certain property in a much more succinct way than in the other logic. Yeah, so one example that we're going to see is the Hamilton path problem, the existence of a Hamilton path. So this could, for instance, be the property, the existence of a Hamilton path. Remember, it was a path through a directed graph that visits exactly every vertex once. We have seen this actually in the last lecture to show that this problem actually is co-NP hard. And we have seen that the LTL, you can express this in a formula which is polynomial in the size of the graph. Yeah. In CTL you can express the same property, but you need a formula that is exponential. Yeah. So you can express the property, but you need a much longer formula. This does not hold for all the properties here, but there are properties which is the case. Now, what is the other important difference? We have seen that this is p-space complete. Yeah. And this is actually model checking problem, and this model checking problem is p-time complete. Yeah, so model checking of CTL is easier, conceptually easier. And now people always say, well, if you have a formula here that you can express in both, you should always use a CTL model checker because it's much faster. This is a stupid idea because, as I just explained, there may be properties that you can express by a formula in polynomial length in LTL. Yeah? But the formula here is exponential. So it's p-time complete, it's polynomial in the size of the formula, but the formula itself for this property might be exponential. Yeah? Good, then we are going to see that here fairness is easy. I mean, there are no free lunches, right? So it cannot be the case that now we have a logic where model checking is conceptually easy, p-time complete even, but fairness will be complicated. Yeah, complicated. Good. So from today on, we're going to be confronted with this thing. Now, there are many more logics. So if you are a logician, then you would say, okay, why don't you take a logic that covers both? Yeah? Makes sense, right? And that's also what I'm going to address, so that we will consider at some point a logic that considers both. So we're going to consider a logic that actually is this. Yeah? Yeah? The best of both worlds, or the worst of both worlds, depends on how you view it, right? This is a logic CTL star. Yeah, and we're going to see that this is strictly more expressive than both. Actually, there are properties here, yeah, that you can neither express in LTL nor in CTL. But of course, there is a price to be paid. The model checking algorithm is a bit expensive. And if you're a true logician, you might say, wow, this is not enough, I want to have even a larger logic. Fine. So there are logics that consider basically more. It can do this. And then you consider things like what they call the modal mu calculus. And I'm not going to introduce you to this. Yeah. And that's also possible. Yeah? So what I'm saying is I'm basically taking two logics out of it, LTL and CTL. Later I'm going to also explain you a bit about CTL star. Why do I do this? Because the model checking of CTL star can use basically IDs of both model checking algorithms, so that's convenient. For the modal mu calculus, this is a completely different story. It would be a completely different kind of lecture. Okay, so far so good. Computation tree logic, Emerson-Clark, 1981. Good, so the observation is we have linear time versus branching time, so we have a transition system. A transition system, if you abstract from the labels, from the actions, because in the end the actions were only used to glue small transition systems together. We only use them for parallel composition. Then in the end we have a state graph and some labeling. In the linear time view, there are state sequences. In the branching time view, there are states and branches. Yeah. So state sequences give rise to traces. You look at the sequence of states, you look at the atomic proposition, that this gives rise to a trace. Here, we're going to look at trees, and they are called computation trees. That's the conceptual difference. So what's a computation tree? A computation tree arises basically by taking a transition system and unfolding it into a tree. Yeah? You abstract from the actions, and you project the states to their labels. So the unfolding is basically given as a tree. So here is an example. Here is an example of a mutual exclusion algorithm. I hope you all have in mind the transition system. Now you can unfold the transition system. How do I unfold the transition system? I start in initial state. If my atomic propositions are crit 1 and crit 2, this initial state is not labeled, empty set. Now two things can happen. We have two threads. Either thread 1 requests access to the critical section, or thread 2. Thread 1 and request to enter the critical section, thread 2. They're both still not in the critical section, so the state themselves, the label of the states is still empty set. But you see the branching. Yeah? It makes a difference. So here, thread 1 has requested access. Now it can access. Now we get to a state where grid 1 holds. Or process 2 also requests. Yeah, and that's the empty set again. And in this state you see the branching. Now both are waiting. Both have requested to enter the critical section. Now either 1 gets access or 2 gets access. Yeah? So you basically take this transition system and you unfold it. If your transition system has cycles, which in this example it has, this unfolding is infinite. So we don't talk about infinite sequences anymore, we talk about infinite trees. But they always have a finite branching degree. Yeah? Every vertex in the tree has only finitely many children. Yeah, because in a transition system I can only have finitely many successors. So we have countably infinite trees, but with finite branching degree. These are the objects that we are considering. Good. And now you can have a path. What is a path? Well, one path is one traversal through the tree. Yeah? So for instance, you start here, which corresponds to this state. Then you go to weight 1 NC2, so that's here. Then you go to crit 1 NC2, that corresponds to there. So now I'm here. And then you can do this, and that corresponds to going there. Yeah? So one traversal through the tree is one trace. Yeah? So basically you can consider a tree is just a representation of a bunch of traces. Good. That's the computation I just showed you. Okay, so summarizing linear time versus branching time, we have paths and we have states. Here we have traces and trees. The temporal logic is LTL, there it's CTL. Model checking, here we have seen it's p-space complete, and the model checking algorithm I showed you via Buggy automata was linear in the size of the transition system, but exponential in the size of the formula. This is in p-time, it's actually p-time complete, and this is the algorithm I'm going to show you in one of the next lectures is linear in the size of the transition system, but linear in the size of the formula. So this exponential blow-up which is there is no longer present in CTL. And we're not going to use Buggy automata, but we're still going to use the expansion law. That's again the most important thing. Implementation relations here is trace equivalent. What do I mean by this? If you give me two transition systems which have the same traces, then they LTL, for any LTL formula, if it holds in one transition system, it also holds in the other transition system. If it doesn't hold, it doesn't hold in the other one. So they correspond, right? This is no longer the case for CTL. So here we are going to have another notion, which is bisimulation. If you want to check whether two transition systems are trace equivalent, so whether they are LTL equivalent, this is p-space complete. This is what stems from checking whether two finite state automata are language equivalent. Also, this is p-space complete. Checking whether two transition systems, two finite transition systems are bisimilar can be done in polynomial time, and actually this is also p-time complete. So this looks all much more friendly. Yeah? Fairness is easy here, and this requires, well, it's not complicated, but it requires a special treatment. Okay? Maybe it's good to know that in the 80s, so all these works came up in the 80s. So LTL was in late 70s, early 80s. This was in 81. And then there were two schools. It was the linear time school and the branching time school. And then there was a whole bunch of papers in the literature, linear time versus branching time. Yeah? And people were really fighting against each other. What is better? Yeah? And actually there is a nice paper, it's by Moshe Vadi. And he says, there's a paper, linear time versus branching time, the final showdown, because he wanted to stop this whole discussion. His view is linear time. No? But the truth is there is no real, it's not the case that one is better than the other one, right? I mean, there is room for both. Both have their advantages, both have their disadvantages. Good. So far about linear time, branching time. So we go to computation tree logic. So computation tree logic can state properties about states. Mentally think about this infinite tree. You can state a property about a state, think about the root of the tree. This can satisfy true. Every state will satisfy true. It can be labeled with an atomic proposition. It can satisfy something which is a conjunction, a negation. And you can say something about there exists a path starting in that vertex in the tree, and that path satisfies a particular property, namely phi. So this small phi is a property about a path, and a path is a sequence, right? Just a path in a tree, infinite path. And you can say something about in this state in the tree, all paths starting there satisfy a certain property. Yeah, so the existential and universal quantification allow you to quantify over the paths starting in, for instance, the root of the tree. What kind of path formulas can we express? Well, this is just like LTL. So you can say something like next something, and you can say something like this must hold until that must hold. Now you have to be a bit careful. The arguments of a next are a state formula. Yeah? It's not an arbitrary path formula. Yeah, so something that you cannot easily write down are things like this. Yeah, so A until B is perfectly valid as a path formula. Yeah. And then you can say as a state formula, well, there exists a path which is A until B. This is fine. No? In LTL, you would also be allowed to say something like A until B until C. No? This is not allowed here. Yeah. Why not? Well, it needs to be a state formula. This is a state formula, but this is not a state formula. So syntactically, we're going to forbid this. Yeah? So this is not in CTL. Yeah? What instead is in CTL is something like this. Well, a path formula that says there exists a path such that A holds until, and now again I need a state formula. And one particular state formula could be of the form for all B until C. This is okay. Yeah, but I'm forced to put a quantification here in front of the until, which here I was not doing. So the way to think about this is that linear, let's say, modalities like next and until must always be directly preceded by a quantification, either being an existential or a universal quantification. And this is forced syntactically. And now you can define things like there exists a path so that eventually phi holds, which is simply there exists a path such that true until phi holds. Here this is something like for all paths true until phi. There exists a box phi, which is something like, yeah, you cannot write this down like this. You may be tempted to do this. Why? Because we know that box phi in LTL is nothing else than not eventually not phi. But you cannot write down this formula, so you cannot write this down in place of question mark because this syntactically is not a CTL formula. Yeah? Same problem as I just have on the board. So, but this is not for all, eventually not phi, and that's a CTL formula. Yeah? So you need to be a bit careful about what to write down and what you cannot write down, because certain things are syntactically simply forbidden. This is then still okay, because this is a thing. The problem is this negation here in front. There is no negation here in a path formula, right? You cannot negate a path formula. You cannot take a conjunction of a path formula. These kind of things are also not allowed. Good. So next until, that's clear. Always eventually, that's clear. So things like mutual exclusion for all box, one of the processes, at most one of the processes in the critical section. Every request will be answered eventually. For every path, it's always the case, if a request is being made, then for every path starting from there, eventually you will get a response. So the way to think about this is in terms of a tree. So we look at the unfolding of the transition system. This is very schematically my infinite computation tree. We say for all paths, take a path. This is a path. For all paths it's the case that always the case that if this is a request, so if this is request, then it must be the case that for all paths starting here, this is one of them, but maybe I could also have gone here. Maybe I can go here. Maybe I can go there. For all of them, eventually there needs to be a response. So that means that on this way there needs to be a response somewhere. But also if I take this path, I need to have a response somewhere. Maybe on this path here is response, but there needs to be a response somewhere. It doesn't always have to be at the same distance of this request, right? But it has to be everywhere. Yeah. So also here, maybe here there is a response. Yeah. And this holds for any request that you have. Yeah. Good. A traffic light. For all computations, it's always the case if the traffic light is yellow, then for all possible computations, the next state must be red. This is an interesting property. We're going to see later and going to prove that you cannot express this property in LTL. So this says the following: for all computation paths, in any state of any computation path, there exists a path that eventually brings you to the start state. So this nesting of universal and existential quantification is actually one of the strengths of CTL. Yeah. Notice that it says for all paths, it's any state along this path, there is a possibility. It's not saying you should take it. Yeah? There is a possibility, there exists a path that eventually goes to the start state. Good. Fairness. This is an easy fairness thing. Unconditional fairness. We're going to see that this expresses infinitely often crit 1 and infinitely often crit 2. And that's exactly what we called unconditional process fairness. We're going to see that the other fairness assumptions are going to be a little bit problematic in CTL. Good. So an example is this, I guess you all know this is this 15 puzzle. So here you have tiles. These tiles have numbers. And there is one tile which is a hole. Yeah? And now you can shift those tiles. So you can shift this one position to the bottom, or you can shift the 9 one position to the left, or you can shift maybe the 7 one position up, right? What is the end of the game? The end of the game is you would like to have this configuration, all the tiles in the right formula. Yeah? We all know that this is a hard problem. There are actually exponentially many combinations, so you have to be a bit careful. This system has 2 times 10 to the power 13 states. That's why children typically give this puzzle to their parents give this puzzle to their children. Then they hopefully have some rest for the couple of time. What's the state? The state is a game configuration. So this is one state. This is the final state. This is a state we want to reach, right? What are transitions? Transitions are the legal moves. So the move that, for instance, I moved this tile 9 one position to the left. This gives me one new configuration, and that gives me a transition. So you can model this, for instance, by some kind of parallel composition. And then the CTL specification is that you would like to check, does there exist a path? Does there exist a sequence of moves, legal moves in the game, such that eventually I reach this configuration? What is this configuration? At position piece I is at field I. If I number the fields, according to the numbers here, then I want to say that this 6 is exactly at position 6, and 7 is at position 7, etc. You put this into a model checker. In particular, what you typically do in a model checker, you put the negation of this formula into the model checker. Why? Because then you say there does not exist. It's not possible to reach this configuration. So what you're saying is it's not possible to move there. And then the model checker will give you a counterexample. And the counterexample is a solution to this game. Yeah? The shortest counterexample is minimal number of moves you have to make to go from this configuration to that configuration. Good. So what I'm saying is you can use model checking to solve games. Good. Okay, semantics for CTL. You can define a satisfaction relation for CTL in the same way as we have done this for LTL, and we take as an input a transition system without terminal states. We have formulas about states, we have formulas about paths, so we have two satisfaction relations. One for the state formulas, one for the path formulas. Good. Remember LTL? For LTL it was easy. We just take paths and we express everything in terms of paths. So for instance, take a look at the next. This path satisfies next phi if and only if the suffix, which means you just delete the first element, this S0 from this path, this satisfies phi. This you cannot do anymore. Why not? Yeah, because it's always next of a state formula in CTL, not next of a path formula. So this will be a relation between a state and a state formula, whereas this is a relation between a path and a path formula. Yeah? And they are in some sense intertwined in some way. So path formulas. We take an infinite path starting from S0. We say a pi satisfies next phi. Phi is a state formula. So this holds if and only if the next state in this path, which is S1, satisfies the state formula phi. So if this says next red, this holds if and only if the next state in pi is satisfying the atomic proposition being red. Until, similar. Again, these two things are state formulas. So we're going to say there exists some kind of position along this sequence. Let's call this position J, such that at position J phi 2 holds, and at all preceding positions K, preceding strictly less than J, we have phi 1. Good. So that means immediately that you have something like if you have eventually phi, eventually means true until phi, then definitely you get something that existed an index J such that that index satisfies phi. And box means simply, as you intuitively would understand, for all J we have that Sj satisfies phi. Good. What about state formulas? Good. State formulas are just is this satisfaction relation between a state and a state formula. Every state satisfies true. A state satisfies an atomic proposition if and only if it's labeled with this. Conjunction is conjunction, negation, negation. Existential path. So a state satisfies existentially, there exists a path satisfying phi. So if and only if there is a path pi starting in S, this is this S, such that that path satisfies phi. And the universal is then similar for each path starting in S, that path satisfies phi. Good, but you see the intertwining. This is the relation between a state and a state formula. This is a relation between a path and a path formula. They are always alternating. Then it's useful to define this notion. It's the satisfaction set of a state formula. These are just a set of states satisfying that formula. So sat of phi is the set of states that satisfy the formula. Good. Then the interpretation of a transition system. So a transition system satisfies a formula if and only if all its initial states satisfy the formula. That means S0 must be a subset of all the states satisfying phi. Good, and that's the same as what I just said. Good. Next. What is next? The next operator says the following. S satisfies there exists a path such that next phi. So first we apply the semantics for existential quantification. So that says there exists a path starting in S. So this path starts in S, such that this path satisfies next phi. But that's nothing else than saying that S1 satisfies phi. So in terms of a tree, this is represented as follows. This S, you can imagine this as the root of the tree. There exists next phi means that this thing has one of its direct children satisfies the formula phi. So in this case, for instance, S1. Or a different way of saying this, the set of direct successors of S intersected with the set of state satisfying phi must be non-empty. Yeah, so this means for all next phi. So in terms of the semantics, it says for all paths starting in S, so for every pi you have to have next phi. So in terms of a tree, this means S again being the root of the tree. For all next phi means for all children of S, phi should hold. So all S children should be, in this picture, colored pink. Until, I hope you understand this difference between existential and universal, and now you see that there exists a path which is blue until red. Is there exists a blue path which until you reach a red state? Of course, there may be plenty of other paths that do not satisfy blue until red, but that's okay. This is a tree that satisfies for all blue until red. So no matter where you go starting from the root, you go here and you reach some red state after 2 transitions, and maybe here I reach it after 3 transitions, and so forth. There exists a path eventually phi. This means there exists a path starting from the root that leads you to a red state, and here is this path. That there are many paths that do not satisfy eventually red, this is all fine. For all eventually phi, yeah, it simply means that everything which was blue here is now not relevant anymore because it's true until phi. So no matter where you go, at some point you reach a red state. Good. So this was for all eventually phi. There exists eventually phi now with box. So there exists a path which is completely blue. So here is this completely blue, and of course in all the pictures it's meant that this goes on ad infinitum. For all box phi, it simply means the whole tree is blue. Yeah. For all paths starting here, all states are blue, and that means simply that the whole tree is blue. Good. Example. So this is the example we have seen plenty of times before. We want to send a message, this message may get lost, then you resend it, and at some time you hope that it will be delivered. So let's look at the CTL formula for all box for all eventually start, and we want to check whether the transition system satisfies this formula. One scheme to do this is that you first look at the subformula. So you look at the formula and you try to reason from inside out. So I start with this subformula, and the first thing that I'm going to ask, which states satisfy that for all paths starting in that state you get to the start state? Well, this definitely is true for start, right? Because you're already there. And this also is true for delivered because all paths immediately go to the start state. But this is not true, for instance, for lost, because you can go into this loop, and the same holds for try. So this is true for the states start and delivered. Okay. Now, mentally think about replacing this subformula by just having this set. Yeah. So I'm interested in for which states now do we satisfy the formula for all box this holds. Yeah. So this is basically what I'm doing, and that means that we are for all box start or delivered. Yeah. Now this is not so hard to determine. So this is actually the empty set, because this says for all paths you always are in the start state or in the delivered state. Yeah, and you can immediately see there is no state satisfying this. So therefore, this transition system violates this formula. Yeah, that's what we just had determined. Good. And this is what it says, infinitely often starts. That's the intuition behind this formula. And it's not the case that for all paths, infinitely often start holds, because you can go here and then stay here, and then you only have finitely often start. Good. So what about infinitely often? So here you have this formula for all box for all eventually A. This says the following. According to the CTL semantics, yeah, it says for all paths, so for all paths starting in S, and now we have box for all eventually A, and it's not difficult to see that this is nothing else than there are infinitely many indices I such that Si satisfies A. And that's the same as the LTL formula, infinitely often A. Yeah, one way to see this is, again, look at the tree. here is a tree. What does this formula says? S, so S is the root of the tree. It says for all paths, so take a path. This is a path. So this is a path. What does it say? It says box, so we have that S satisfies for all box for all eventually A. If this is path pi, then pi satisfies box for all eventually A. No? I just strip off this first quantification. So what does that mean? It means basically that if pi is a path S0, S1, S2, etc., yeah, it means because of this box that for all j, Sj satisfies for all eventually A. Yeah? Good. So take such a state. Let this be Sj. Good. This is one of those states in pi, so it satisfies for all eventually A. What does that mean? Well, in terms of a tree, you're going to look at the subtree which is rooted at this state. This is the subtree rooted at Sj. This contains all paths there, so it contains all the paths. Take such a path. Take a path in this subtree. For instance, pi prime. What does pi prime satisfy? Well, pi prime needs to satisfy eventually A, yeah, because of this. So it means that along this path there needs to be some A, yeah, here. The same holds, of course, for this path, the suffix of pi that starts from Sj. Also along this path I need to have an A. And this reasoning is applicable to every Sj. So in particular also to this guy. Yeah? But also to, for instance, this guy. All S's along pi. But that means that you have to visit infinitely often an A. Yeah? Good. A somewhat more involved transition system. Start, try, lost, error, delivered. I want to check whether the transition system satisfies this formula. With CTL, I never try to pass the formula. The strategy is always the same. You look at the most nested subformula, the most nested state formula, which is, let's say, satisfied. So we start with this yellow subformula. Yeah? Now, this yellow subformula says for all paths, always not start. So which states satisfy this property? Well, definitely this state does not satisfy the property because every path starting here is a start state. So what about this? No, because I can go from try, yeah, to delivered and from delivered to start, and therefore I'm refuting the not start thing. So try is also not satisfying this property. Similarly, lost is not satisfying the property because I can go from lost to try to delivered to start. Yeah. So basically I'm looking for states that cannot reach start. There is only one, which is the error state. Good, so now I replace, again, conceptually speaking, this yellow part by means of this formula. So now the formula becomes a little bit more friendly. Does there exist a path that leads me to the error state? Yeah. Good. So I'm interested in which states satisfy this formula, which corresponds the same to which states satisfy the original formula. Good. Which states are satisfying there exists a path that eventually error holds? This actually holds for all states, because every state can reach finally the error state. And that in particular means also the initial state satisfies this, and therefore the transition system satisfies this formula. Yeah. Lesson learned. Read formulas from inside out. Yeah. That's the way to look at this. Here is an even more complicated formula. I don't want to even think about it. Yeah, for all next there existent, next that for all box something holds. Boof. Inside out, right? For all box start, not start, which is exactly the same subformula as we just have seen, which were all the states that could that never can reach start, which is only the error state. Okay, so that simplifies the formula to this. Now, which states satisfy there exist next error? Well, definitely error itself plus try. right? Because try has one transition into error. Good, but now we can simplify this, because now this becomes this formula, and now life becomes more friendly. And now you check which states satisfy this formula. For all paths, the direct successor is an error or a try. Well, this, for instance, holds for lost, because it only has a try or error. For try itself, it doesn't hold, right? Because you can also move to delivered. So what do you get? You get at the end the error, lost, and start. And start, it also holds, because start only has one successor, which is try, which is satisfying this disjunct. So that's okay. So the initial state is included in this set, and therefore the transition system satisfies this formula. Yeah? Good. This is another example. We're going to skip this. I guess you got the idea. Yeah? So here is an example of a very simple transition system. The question is, does the transition system satisfy the following problem, the following formula? There exists a path such that from the next state on, all paths never satisfy A. Good. How to deal with this? Same recipe as before. Answer will be no. Why? Look at the inside formula. Look at this subformula. For all paths, you never have an A state. Now, this is not satisfied by this because it's an A state, and it's also not satisfied by this because I can move to this blue state. So the only state satisfying this formula is S2. So now I can say there exists next S2. Which state satisfy there exists a path so that the next state is S2, S2 itself plus S1, but not the initial state, and therefore the transition system violates the formula. Good. And there are other examples, but we're going to skip this. I think I'm going to skip this. Good. What about the following statement? We have a transition system and a CTL formula. If T violates not phi, then T satisfies phi. Is this true? The answer is no, because T satisfies phi means all initial states satisfy phi. It means that if you refute not phi, it means there exists an initial state that is not satisfying not phi, but it's not saying that all initial states satisfy not phi. Good, so that's the same thing as we have seen in LTL. Good, so here you have an example, a transition system with two initial states. This does not satisfy the formula there exists always A, yeah? Because this formula has to be true for all initial states, but for this initial state there does not a completely green path. But this transition system also doesn't satisfy the negation, because this is an initial state that satisfies there is a path which is completely green. Good. Hamilton path problem. Finite directed graph. Does G have a Hamilton path? That is, there exists a path that visits each node exactly once. Idea is we want to encode this in CTL. So that's exactly one of these problems that we have seen here. We know how to encode it in LTL. Yeah, in LTL this was easy. What was the Hamilton path in LTL? So Hamilton path in LTL, it says something like, eventually you have to reach a vertex, and it's always the case that if you have reached the vertex, you should never visit it again. So it should always be the case that from there on you never visit V again. And this you have to do for all vertices. So this is something like the formula. Yeah. So this is a polynomial in the size of the graph. In CTL, this is a bit more awkward. Why? Intuition, I have to always indicate the branching. Is it there exists or is it for all? So what I want is I want a finite digraph. I want to obtain a finite transition system and a CTL formula phi such that G has a Hamilton path if and only if, now in this case the negation, TG has not a phi. So in terms of LTL, the non-existence is of course given by just the negation. Good, so I want to show this, the transition system does not have an Hamiltonian, that means doesn't satisfy phi. So how I'm going to do this, this was the example, same principle as before. We just take the transition system as being those three vertices. Every vertex is an initial state, and we have a trap state. that once you have traversed the graph and visited every vertex exactly, you end up in this trap state. Exactly same construction as last week. And now what is the CTL formula? So now the point is that you have to encode all possible orderings. So one possibility is you can either start in V1, in V2, or V3. So here we start in V1, here we start in V2, there we start in V3. Okay, so what can happen? Well, from V1, there are possible orderings. Either after V1 you visit V2 or V3. Yeah, you have to encode all possible possibilities. Here, of course, there is no possibility to go from V1 to V3, but I want, of course, a formula that is applicable to every graph. Yeah. So I'm going to say I'm currently in V1, and it is possible that my successor will be V2, and after V2 there is a possibility that the successor of V2 is V3. Or after V1 the direct successor is V3, and there is a possibility to get V2. So what you see, I have to list all possible orderings. Yeah. And this leads, of course, to a formula which is exponential in the size of the graph. Yeah. So this is an example of a property which is there, but it's to formulate that property in LTL leads to a much more compact, shorter formula than in CTL. Good. And the negation, because I was interested in the negation, is just the negation of this formula. That's the same as in LTL. Good. Now we get to, like for LTL, we get equivalences. So when are two formulas equivalent? And we define this in terms of state formulas. So state formula phi1 is equivalent to state formula phi2. If and only if for every transition system T, T satisfies phi1, if and only if T satisfies phi2. And that means that you quantify over all the transition systems. That's the same as saying for all transition systems, the set of states satisfying phi1 coincides with the set of states satisfying phi2. Good. Trivial examples are things like this. I don't think I have to spend many words on this. Other examples are next. So what do we know about next? Well, in LTL we know it's dual, right? So in LTL we know that something of the form next, not next phi was equivalent to next not phi. Now we can push the negation inside. The same is true here, but now you have to keep track of the quantification, so not for all next phi. So it's not the case that all direct successors satisfy phi, which means there exists a direct successor that doesn't satisfy phi. Makes sense. The same for, of course, existential quantification. If here's an existential quantification, this becomes a universal quantification, and you can push the negation inside. What about this? There exists a part eventually A and B is equivalent to there exists a part eventually A and there exists a part eventually B. This looks to me like nonsense, because there is an existential quantification. Eventually is also something like exist. And we know that conjunction does not distribute over existential quantification. So this is wrong, and here is a counterexample. There exists a part that eventually goes to blue. There exists a part that eventually goes to red. But of course, there does not exist a part that goes to blue and red at the same time. What about this? For all eventually A and B is equivalent to for all A and B. This is also not true. What's the intuitive way to see this? This is a universal quantification, but this is an existential quantification, right? There exists a position somewhere. And here is the counterexample. For all paths, eventually you get to A. Well, here, for all paths, eventually you have to pass through this state. So you eventually get A, you eventually get B, but of course you never get to a state which has A and B. Good. What holds is the following. Equivalence is like this. And the intuition is relatively simple. This is a universal quantification. Box is a universal quantification over all states. You know that conjunction distributes over universal quantification, so therefore it distributes over for all box. This is an existential quantification. This is an existential quantification. Disjunction distributes over existential quantification, so we have this equivalence. Good. What about this equivalence? This is correct. How to see this? Yeah, in terms of a formula, it's for all direct successors. Think about the root for all direct successors. The next states, so the children, for the children says for all box A. What was for all box A? The whole subtree is blue. So for this child, the whole subtree rooted here is blue. The same holds for this one and the same holds for that one. That's the formula on the left. The other one says for all paths starting here, it's always the case that all direct successors satisfy A. Now this is true here because all direct successors satisfy A. Now take a path, for instance moving here, and then of course here also all direct successors are blue. Now move here, all direct successors are blue because the whole subtree is blue, and therefore you get that these two formulas are equivalent. This existential quantification two formulas is not the case, so this is the same formula as on the top of the slide, but I changed both universal quantifications by existential quantifications. This is wrong. Look at the following transition system: yellow, blue, yellow. Claim S0 does not satisfy there exists a path such that from the next state on there exists a path which is completely blue. Look at S0. Does S0 have a computation such that when it goes to the next state there is a path which is completely blue, which is not the case because, for instance, you can move here, and then this is not satisfied. There exists a path which is completely blue. Also here, what about this path? This is another possibility. You can stay here. Does it satisfy there exists next or eventually existent always blue? This is also not the case. So no matter whether I take the self cycle or I take the self cycle finitely many times, for instance 0 times, and I move to the right, this not satisfies next existential box A. So more systematically, again look at the subformula. There exists box A. There is no state satisfying this. So actually it says there exists next false, and therefore it cannot satisfy. But S0 satisfies the following formula. There exists a path such that always along that path there exists a next state which is blue. Now, which path would satisfy this formula? So in S0 we have to find a path such that in any position along that path there is a next state which is always blue, which is blue, not always. So take the path which takes this self loop infinitely often. This is definitely a path starting in S0, and it satisfies box. Every time you are in S0, S0 has a next state, so there exists a next state, which is always A. So I take the path S0 omega, thus take the self loop. This S0 omega claim satisfies box existential next A. Why? Because S0 satisfies there exists a next state which is A. I hope that's clear. And what is now the weird thing, and this is something that you should keep in mind, is that we are reasoning. We have to check this formula. The reason why it satisfies this formula is a path that itself never reaches a blue state, but it has the possibility to move by one transition to a blue state. And it's this possibility which is expressed by this existential quantification that sometimes makes reasoning a bit more harder. You reason about a path, and in order to satisfy this formula, you have to reason about the possibilities along this path, so you also have to include this outgoing arrow that you never take, but still is an important role to check whether the formula holds or not. This is why some people argue, Moshe Vardi, Leslie Lamport, the world is linear because it makes life simpler. And especially because of this reason. Good, this is what I just expressed, so I'm not going to this. Then you can define things like weak until. That goes very similar to for LTL. So in LTL, what was weak until? A weak until says green unless blue, says it's green until, in particular, at some point we establish blue, or always green. In CTL, it looks, and then you have a duality between until and weak until, as we extensively have discussed. And in W, you can also define it in CTL, but now you have to define things like existential W. Now, existential W is something like the negation of an until formula, because, yeah, something with, they are dual. So what you get is W can be defined in terms of until, but now what you have to do in order to get the existential quantification, you get a negation of the universal quantification. Good. And the same for universal until. Good. I'm going to skip this because I think it's not so important. What I want is I want to go to the expansion law. Yes. Because that's the crucial part, again. So remember the expansion law for LTL. Yeah, so for LTL we have something of the form phi 1 until phi 2 was equivalent to phi 2 or phi 1 and next phi 1 until phi 2. We have said this is an equation where this formula occurs on the left and also on the right, and therefore it can have many solutions, and we have seen until is the smallest fixed point, the weak until is the largest fixed point, and so forth. So now I want to lift this to CTL. Yeah? So the first thing is that we need to have something with a path quantification, because this is not, let's say, a state formula. And so what I want is I want to have something like there exists phi 1, I should not write this down, I would write phi 1 until phi 2. Yeah? These again are state formulas. And now the principle is very much the same. So this is equivalent to, well, when is this satisfied? If the current state satisfies phi 2, then we're done. Yeah? If this is not the case, then the current state should satisfy phi 1. But now, we need to satisfy there exists until from somewhere on. So what we get is there exists a path such that from the next state on, the until formula is satisfied. So we get there exists phi 1 until phi 2. Yeah. So here, this formula here, you see this back here. Yeah. That's the same as in LTL. But now because of this existential quantification here, we get this existential quantification there. Yeah. And the way to view this intuitively is, again, think in terms of trees. This is a tree, very abstract. I want to satisfy for the root. Yes. We want to check there exists a path. Let's do this with atomic propositions, A until B. Yeah, good. Now there are two ways to fulfill this formula. If this state is B itself, we're done, because it has a path, namely the empty path, that satisfies this formula. If this is not the case, well, then it definitely has to fulfill A, so phi 1. But then it means that it has several successors. Let's say there are 3 direct successors. And then for at least one of these successors, you need to still establish there exists A until B. So maybe this is a successor, which is the nice one, then maybe from this one on, I have to fulfill there exists a path at A until B. No? But it's enough that there exists such a thing. I don't have to, let's say, request this from all possible things. So what would you get if you get a universal quantification? Well, very similar. The formula is fulfilled if the current state establishes phi 2, or otherwise you have to fulfill phi 1. And now for all possible successors, we need to fulfill this formula, phi 1 until phi 2. Yeah. So the same as now I have this universal quantification, I get the universal quantification there. Yeah. If you have understood the expansion law for LTL, this, I hope, should not be that much of a big deal. Good, so this is also on the slide which I already, and now you have the simplified versions of it. If you just have true, then as for LTL, things become simpler, right? Because if you say there exists eventually true until psi, it means that this is vacuously true. And that means that you can simplify things because this is deleted and you get psi, or, and then there exists a next state such that this establishes this formula. Good. The same you can do for weak until. So as for LTL, here you have existential until, existential weak until, and they both satisfy this same equation. Similar or same as for LTL. Good, the other things are all simplifications. So here is the things for weak until. Here is existential box phi. There exists a path which is always satisfying phi, if and only if the current state satisfies phi, and the current state has some successor for which that successor has a path which is always satisfying phi. Good. Are there any questions so far? Silence. Good. Dualities of box and eventually, I'm going to skip this. This is all. Good. What is important is the following. We have universal quantification and we have existential quantification, and for the algorithms later on, the model checking algorithms, we're going to restrict ourselves to what we call the existential normal form. What's the existential normal form? It says for every CTL formula there is an equivalent formula that only contains existential quantifications, so no universal quantifications. So we have operations of propositional logic, and we only have there exists next, there exists until, and there exists box. I need now exist box because I cannot write it down as not for all eventually, because there is no universal quantification. So I have to take it as a basic ingredient here. So this is the syntax of CTL in existential normal form, the standard propositional logical fragment, plus there exists next phi, there exists phi 1 until phi 2, there exists box phi. Good. Is this a restriction? No, this is not a restriction, because every CTL formula can be transformed into an equivalent formula in existential normal form. For instance, this is a formula which is no longer allowed because we don't allow universal quantifications, but this is equivalent to not existentially next not psi, and here is a formula in existential normal form. What happens for a universally quantified until formula? You use the duality with the weak until. So for all psi 1 until psi 2 says there's not the case that there exists a path for which not psi 2 holds until not psi 1 and not psi 2, and it's not the case that there exists a path which never establishes psi 2. The last part is hopefully clear. I mean, you have to establish psi 2, so there should not be a path that never establishes psi 2. Yeah. And this says basically that it should not be the case that there should not be a path such that you have not psi 2, so you violate, let's say, the right-hand side, until you violate both, and that's also bad. Good. So here is an example, a universally quantified, well, two universal quantifications. The first thing is we get rid of the universally next operation. Here I do it the other way around. I first did the until, so you first take this equation. So you plug this formula into this equation. Here we get not psi2. Psi2 is not C, so therefore I get not C, and so forth. Now I can simplify this a bit. This is the simplification. Now I can push this negation inside, or use this equation up here. So this is the formula over here. And this is the equivalent formula in existential normal form. Okay, you can do similar things with positive normal forms, but that's not essential here. So what we're going to do, starting from the next lecture on, I'm going to introduce you first, going to explain much more in detail this picture. So we're going to talk about the expressive power of CTL versus LTL. We have seen already some examples there. We have seen, for instance, the example that for all eventually A is equivalent, so this is a CTL formula, but this is equivalent to the LTL formula infinitely often A. One of the things that we're going to see next week is if you swap the order, so if you say instead for all eventually for all box A, I just swap the diamond and the box, we're going to see that you cannot express this in LTL. You would be tempted to say, wow, this must be something like equivalent to this, and we're going to see that this is not the case. This is actually a property that you cannot express in CTL, and the other thing is a property that you cannot express in LTL. Okay, if there are no questions, which doesn't seem to be the case, then thanks, and hope to see you back next week, Tuesday morning, early.